Assalamu alaikum and good morning, everyone. Before we continue with the exercise where we stopped at, I would just like to recall a few things that you need to know about the electrochemical cells. Electrochemical cells is when you combine the two half cells, and the difference in voltage or the difference in electrode potential between the two, we call it the cell potential. A few things, what you need to know first and foremost is the most positive half cell will become the positive electrode, okay, automatically, and reduction will happen on the positive terminal or electrode. The most negative, or whichever is the less positive, it doesn't have to be a negative number, will then become the negative electrode, and oxidation will happen in this negative terminal. So the flow of electrons is also from the negative electrode to the positive electrode, because the negative electrode is where oxidation is happening, where you lose electrons, you give away electrons. So where the electrode that has oxidation reaction happening, this electrode will supply the electrons needed for the reduction reaction, because reduction is the gain in electrons. Okay, so we'll go back to the question that we were doing, that is to practice the drawing of a cell, and then we've also looked at the reaction that is happening at each electrode, making sure that we've labeled the electrode correctly with the correct pole, whether it's the positive electrode or the negative electrode. We've also labeled the standard conditions for the setup, and we also found the E cell. Now, the calculation that I have, the working or the expression that I use for my E cell is different from the one that you see in textbooks, okay? The reason for this is because I have already changed the value of the electrode potential. I changed the sign whenever I am reversing the reaction, okay? All right, part 2 of question 3, we are going to look at the chromium 3+ chromium half cell and a chlorine chloride half cell. So first things first is to look at their standard electrode potential value. Chromium should be at C, and we want the chromium, what was it again? Sorry. Chromium 3+ and chromium. So we want this half cell. Copy. And then we'll just paste it somewhere here. And the other one that we need is of chlorine, Cl2 and Cl-. So that is under C as well. So make sure you get the correct half equations. Okay, so once we have this information, we can then, oh, I can no longer move it. Okay, draw a diagram of the electrochemical cell. So we already know our two half cells. So start with the easier one, which is a chromium Cr3+ and Cr metal. So when you are drawing the diagram, make sure that you follow the correct state symbol of the species you have in the half cell equation. So chromium Cr in its standard state or standard form is a solid. So The only way that we can introduce solid chromium is by making it the electrode. Chromium 3 plus would be in ion form. So that means we have a Cr3 plus because it is a standard, in a standard condition. We need the chromium 3 plus to have a concentration of 1 mole per dm cube. Don't forget, you will always have that salt bridge, or if you want to lift this to the very last is also fine. Okay, so I've got chromium solid and I've got chromium 3 plus done. Next, I want to move on to my next half cell, which contains Cl2 and Cl minus. Now Cl2 is a gas. It would have to be introduced into the setup via a gas. Maybe I'll just do that. Okay, so usually that's where my Cl2 gas, and because it is at standard condition, it would have to be in 1 atmosphere. And then I've got the solution, making sure that the salt bridge is touching the solution, and that solution must contain 1 mole per dm cube of chloride ions. Okay, and then I connect the whole setup through a voltmeter to read the voltage reading, or the EMF, or the potential difference between these two half cells. Okay, now you notice that even though I've got my chloride ions and chlorine in the drawing, the circuit is not connected yet. It is not a full circuit because chlorine and chloride ions, most importantly chlorine being a gas, we have to make sure that it comes in contact with the chloride ions. So that means we have to use an electrode that is inert. We use platinum electrode. So now we can confidently say the salt bridge connects the two solutions. The ion will be in contact with the chlorine gas on the platinum surface. We've got the wire going through the voltage, the electrode, which is made up of chromium, and the chromium is in contact with the solution, and the salt bridge on the other side is also dipped into the solution. So you can see that there is a complete connection in the setup. Okay, so that, oh, another thing is room temperature 298 Kelvin because they are in standard condition. So that's how you draw an electrochemical cell or an electrochemical diagram, making sure that you go through each species in the half cell equation. Use the data booklet to calculate the cell voltage of the electrochemical cell. So basically, they want you to find what cell voltage is E cell. Okay, before we can do that, I would like to label our electrodes first. So you can see that the chlorine chloride half cell is more positive than the chromium ion chromium half cell. So that makes your chlorine half cell the positive terminal, and automatically the chromium becomes the negative terminal. And as we all know, on the positive electrode, reduction happens, which is the forward reaction. So we will write it as chlorine plus 2 electrons to form 2 chloride ion, and the electrode potential associated with that is positive 1.36. We've got a reduction reaction happening. And on the opposite side, where the negative terminal is, we've got the oxidation reaction, which is the reverse in the equilibrium. So that means our oxidation reaction equation is written as chromium to be oxidized into Cr3 plus and 3 electrons. So you can see that from the negative terminal, we are giving away electrons, and at the reduction terminal, we are taking electrons. So whatever electrons given out on this negative terminal will be moved to the positive terminal and to be taken in by the chlorine gas. Okay, so when we write down the overall equation, you have to make sure that the number of electrons match, even though the question doesn't ask for writing down the whole equation here, but you need to learn how to write down the whole equation before you can combine the half equation of oxidation and the half equation of the reduction. The number of electrons must be the same so they can cancel out. Okay, but that's not being asked in this question. And also I forgot to mention that the electrode potential value associated with the oxidation reaction is now positive 0.74. The reason why I have written it down as positive is because I'm taking the reverse reaction, so I have to change my sign. Okay, so to find the E cell is just basically reduction plus oxidation, which is 1.36 plus 0.74. You will see in most textbooks or everywhere on the internet really that the expression is written down as reduction minus oxidation, okay? Which will give us the same answer. The only difference is that we take it as a addition because we have changed the sign. If you didn't change the sign, it will be the same thing. You take reduction minus oxidation. So that's a negative combined to become positive, which will give you the same answer as well. So that is 2.1 volt. That's the E cell of the whole setup. Okay, state which cell is the positive pole. We've already done that. Predict the direction of electron flow in part A. So it flows from the chromium half cell to the chlorine half cell. Okay, you can either draw it in the direction. Just make sure you label flow of electrons. It makes sense because at the negative terminal, chromium metal is giving away electrons as it undergoes oxidation reaction. Okay. Next, if you want to copy this down and if you need more time, please pause this video. We'll move on to the next part now, which is the Mn2 plus Mn half cell and a Pb2 plus Pb half cell. So luckily we've already got a ready-made diagram. All we have to do is labeling, but we have to make sure that we've got the correct half cell. Manganese would be under M, so it is the Mn2 plus Mn, half cell and nothing else. It's not the Mn2 plus Mn3 plus. Copy. So I just like to have everything on the same page so I don't have to keep on flipping pages. The other one would be the Pb2 plus and Pb half cell, which we have here. Okay, so it doesn't matter where you want to put the manganese half cell or the lead half cell. There is no rule saying the positive has to be on the left side, the negative has to be on the right side. Now, this is an example where you have a both negative number. Okay, so but between these two, the more positive is the lead half cell, so that becomes our positive terminal, and the more negative will become our negative terminal. Okay, so we start with maybe with lead. All right, again, as I said, it doesn't matter where you put the positive terminal and the negative terminal. Now, Pb as a solid will be your electrode, and we need Pb2 plus ions, and that will go into the solution as an aqueous ion with a concentration of 1 mole per dm cube. So we're done. Don't forget to label your salt bridge. And then you need a voltmeter. Well, a voltmeter should be in circle, okay? Sometimes you don't even have to label the voltmeter because it is kind of a universal symbol. We now move on to the other half cell, which is our negative terminal. Manganese is a solid because it's a metal, so that automatically becomes our electrode. And Mn2 plus will be the ions that we need in the solution, and the concentration would be 1 mole per dm cube and 298 Kelvin. Even though there is no gas here, we will just write down what atmosphere as a habit, okay? But even if you don't write it down, you will not get penalized, I hope, because there's nothing that is involving gases, okay? So as mentioned earlier on, the Pb electrode will become the positive terminal, and the Mn electrode will be the negative terminal, okay? Same thing. We are going to write down the equation that is happening on each electrode. I will start with manganese first because it is a negative terminal. Oxidation will happen. So we have manganese being oxidized to Mn2 plus 2 electrodes, 2 electrons, and the E note is positive 1.18. Do not forget to reverse the sign because I have reversed my equation. And then at the positive terminal, it will be the forward reaction. I'll use red. The forward reaction where Pb2 plus will gain electrons to form Pb solid. And as you can see, electrons are being produced on the negative terminal, electrons being used up in the positive terminal. That means the negative terminal must supply the electrons. Electrons flow from the negative terminal to the positive terminal. Okay. E cell, sorry. Pb2 plus undergoing reduction to Pb, the E electrode potential is negative 0.13. Okay, so to find the E cell, we take reduction plus oxidation, which is negative 0.13 plus 1.18, which should come out as 1.05 volt, okay? If they want you to write down the overall equation for the reaction in the cell, this two half equations have the same number of electrons, so they will cancel out. You don't have to multiply the number, but you just add the reactants together, Pb2 plus Mn plus 2e, to form the products Pb, Mn2 plus and 2e minus, and you will see that they cancel out nicely. Okay, so I'll just show it to you once. Overall equation, Pb2 plus 2 electrons plus Mn to form Pb plus Mn2 plus 2 electrons. When you add equations, half equations together, you just put everything on the same side. If it's a reactant, put it on the reactant side. If it's product, you put on the product side. So you can see that the electrons, the two electrons are balanced on each side. We can cancel that out. So the overall equation for this reaction is Pb2 plus Mn to form Pb plus Mn2 plus, and it's not that obvious, but Pb2 plus going to Pb is actually an oxidation reaction, and Mn to Mn2 plus is Pb2 plus to Pb is a reduction reaction, and Mn to Mn2 plus is an oxidation reaction. Now, without the electrons, it would probably not be easy for you to see that. A quick way of seeing if the species is oxidized or reduced is by looking at its oxidation number. So Pb2 plus is +2, Pb is 0. So you go from +2 to 0, that's a decrease in oxidation number. Therefore, it is a reduction process, okay? Which is why it's important for you to be able to work out oxidation number really quickly. You don't want to spend like a good 5 minutes on working out oxidation number. Okay, this is a diagram that you don't have in your notes, but it's okay. It's a comparison between an electrolytic cell, which is your electrolysis setup, and electrochemical cell, which is what we have just looked at all this time. Another name for electrochemical cell is galvanic cell. So if you look it up on the internet and you see galvanic cell, then that is electrochemical cell. Okay, so what you have in the electrolysis is that the current from the power supply is what pushes the chemical reactions to happen. Okay, so at cathode, it will be reduction, and at anode, it will be oxidation. Whereas in a galvanic cell, it is the reaction that pushes the electrons in the external circuit. Okay, there's no power supply, there's no nothing, but because of the equilibrium between the two species in different oxidation states, it pushes the current to flow. Okay, it produces some voltage in this setup. So that's the difference. This is why we say in electrolysis, we convert electrical energy to chemical energy. Chemical energy is when you have a chemical reactions happening. Whereas in electrochemical cell, you've got an chemical energy being converted to electrical energy. Okay. Another difference is also in the flow of electrons. Okay, so I think here's another diagram again of the electrolytic cell and the electrochemical cell. I don't know if you remember this. I mentioned that electrochemical cell is sometimes called a battery. So this is actually the basis of a battery. Power supply or energy, electricity, is produced by the oxidation and reduction reaction in each electrodes. Okay, so in electrolysis, we say that oxidation is happening at the positive anode, okay, and reduction is happening at the negative cathode. So the flow of electrons in the electrolysis is, of course, from where oxidation is happening, because that's where you supply electrons, okay? So you go from positive terminal to the negative terminal. Whereas in electrochemical cell, the flow of electron is from negative terminal to positive terminal. So that is another main difference between an electrolysis cell and an electrochemical cell, or also known as galvanic cell. Now, I have removed the anode and cathode because I don't like calling them anode and cathode. This would be your anode because that's where oxidation is happening, but it's confusing because now your anode is a negative terminal. So I would rather just label them as positive and negative. Okay, I hope that's clear for you, the difference between electrolysis cell and an electrochemical cell. Next, we're going to look at what is the use of these E naught values and eventually the E cell. Why do we want to find the voltage? Why do we use the electrode potential values? The first one is that our E naught can tell us about the strength of the oxidizing agents and reducing agents. Earlier on, I've already mentioned that when you arrange your electrode potential values from the most positive to the least positive or to the most negative, you can sort of identify who your strongest oxidizing agent and the weakest, and also your strongest and weakest reducing agent. Now, the way that your electrode potential values are written out is that we always have the reduction reaction written as the forward reaction, okay? So any species that is oxidized, which is anyone who is on the left side, any species who is reduced, okay, which is the people on the left side, is called the oxidizing agent, okay, because they get reduced in the process. If we're looking at the forward reaction, they get reduced. And anyone who is on the right side, on the product side, is called a reducing agent, because what happens to them in reverse, they are being oxidized, and that makes them a reducing agent. So just remember, whoever, for example, oxidizing agent oxidizes another person, but itself gets reduced. So that's chlorine here. Chlorine is being reduced to chloride. That makes chlorine an oxidizing agent. Whereas magnesium solid is being oxidized to magnesium 2+ ion, and that makes our magnesium a reducing agent, okay? And the E naught values tell us a lot of things about which reaction is being favored. The most positive E naught means we are favoring the forward reaction. That means chlorine likes to be reduced. And that also implies chlorine is a strong oxidizing agent, okay? Whereas the most negative E naught means this reaction is favoring the reverse reaction so much, okay? It implies that magnesium is easily or most likely to be oxidized, which makes magnesium a strong reducing agent, okay? So that's what I have been saying. And this was also mentioned to you already earlier. Now, why is it important for you to know whether this species is a strong oxidizing agent or a strong reducing agent? Is because of its involvement in a reaction. If it's a weak oxidizing agent, then probably it is not going to react, okay? For example, like Mg2 plus, if you expect Mg2 plus to be reduced to Mg, it probably doesn't want to happen because it's a weak oxidizing agent. And also the negative value suggests that this reaction is not being favored, okay? So if you only favor one side of a reaction, whether you favor the forward, obviously the reverse reaction will not be favored. You can't have in an equilibrium both the forward reaction and the reverse reaction is being favored, then it doesn't, that just means they're in equilibrium, okay? Okay, so another way of looking at it is strong oxidizing agents have high positive anode and therefore they are easily reduced by gaining electrons. It's true. Chlorine is easily reduced to chloride. Strong reducing agents, okay, which is the bottom right, have high negative anodes and are easily oxidized by losing electrons. So magnesium loses electrons because it is most likely to be oxidized to Mg2 plus. Okay, so this arrangement, provided that you arrange them according to the most positive, according to from the most positive to the most negative, top left species will be a strong oxidizing agent and it decreases as you go down. Bottom right will be a strong reducing agent and it decreases or reduces as you go up. So I will just highlight your strong oxidizing agent, top left, strong reducing agent, bottom right. Okay, so bottom right. Now this rule only applies provided that you arrange their E0 values. Okay, and this is the top left. Okay, so what the E0 values can tell you is already, so you can see between zinc and magnesium, magnesium is a better or a stronger reducing agent compared to zinc. And you can see that silver is so weak as a reducing agent that it does not get, it probably doesn't want to get oxidized, okay? So from here already you can see, if you want to compare between the metals, magnesium is the one that will most likely be oxidized, and hence it's the strongest reducing agent, and silver solid is the weakest reducing agent. As for I don't have, it's just chlorine here, so I don't have anything to compare, okay? But you can already see how this E0 value tells or says about the reactivity of either metals or chlorine, okay? Okay, the second one, the E0 values can also predict the direction of electron flow in a simple cell. So this is something that we've already done. Electrons will flow from the negative electrode to the positive electrode. Please bear in mind that the electrons only move through the wire. So that's why we call it external circuit, not through the electrolyte, not through the solution, okay? So let me just refer to the diagram here, okay? So electrons will travel through this wire and into the electrode. You do not have electrons traveling via the salt bridge or whatsoever. Okay, so that's what it means by external circuit. Okay, here it only travels in the external circuit from one half cell to the other half cell. Okay, so this is just a recap of what you already know. This is new. Okay, E-cell can help us to predict the feasibility of a reaction. If you remember from topic number energetics, where we looked at delta G, how to predict the feasibility of a reaction. Feasibility means, is the reaction going to happen spontaneously? Will the reaction happen on its own, okay, without any external factor, right? Okay, so E-cell can predict the feasibility of a reaction. So feasible means it is likely to occur. Generally, the rule when your E-cell is positive, then the reaction is thermodynamically feasible. That means energetically it is feasible, but whether it happens in real life, we don't know until we carry it out. Okay, so that means in theory, it can happen, right? Another idea that you need to be familiar with is that stronger reducing agent will react with stronger oxidizing agent. Okay, so of course, if it's a strong whatever oxidizing agent or a strong reducing agent, that means they are most likely to either be reduced if you're an oxidizing agent, or most likely to be oxidized if you're a reducing agent. Okay, so we need this strong combination. Okay, if the forward reaction is feasible, the reverse reaction is not feasible. Okay, I will talk about this later when we do questions. Now, what is the limitation about, there is of course some limitation to the E-cell or E-note values. Now, E-note values gives no information about reaction rates. We cannot say that the reaction is fast or slow, but we can say that the reaction will happen or will not happen, or will favor the forward reaction or will favor the reverse reaction, but nothing about the kinetics, the speed of the reaction. And also it only apply to standard conditions. So once you change the concentration, then of course, things will change. So even though E-cell calculated is positive, which in theory and thermodynamically it is feasible, some reactions may not happen because one, maybe they have high activation energy, and secondly, we don't know that in practical the standard conditions are not being met. Okay, as much as we'd like to get as accurate as possible, sometimes the concentration will change, the temperature will change, and this will affect the value of your E-note value. So, and then eventually it will affect your E-cell. Okay, if you don't already remember, E-cell is equals to E-note reduction plus E-note oxidation. So whatever, if your E-note is affected in value, then of course your E-cell will be affected as well. Okay, another reminder is that when you multiply the equation, this is the case for when you want to balance the number of electrons, okay? When you combine the two half equations to get a full equation, which I will show in the next part, the E-note does not change, okay? So for example, if I started with 1 electron in this half equation, the E-note is 1.36. If I multiply the whole thing by 2, which gives me 1 Cl2, 2 electrons, and 2 Cl minus, okay? So you can see that the E-note values is still the same. It doesn't change, okay? So which is different from delta H. If you multiply your equation, your delta H will also be multiplied. So you have to be really careful there. Okay, we will do one question before we go. Okay, will bromine oxidize silver to silver ions? Now here are the steps that are not provided to you in the exam, but it's just a good steps or guidelines for you in practice. Okay, now before I go through the steps, I would like to do this quickly first. Okay, I am going to use the strong oxidizing agent and the strong reducing agent method. Okay, so you can see that my E naught values are not arranged from most positive to negative. Okay, but still, because this number is the more positive number, so that means bromine is more likely to be reduced. Okay, so that makes bromine a stronger oxidizing agent. Oxidizing agent. Okay, whereas my silver plus and silver ion half cell, now even though it's not negative, but it is less positive than the bromine bromide half cell, which suggests that this half cell favors the reverse reaction. Okay, which means that Ag is a strong reducing agent. Okay, so we're going to see, is bromine going to react with silver? So you see, bromine Br2 and silver is a combination of a strong oxidizing agent and a strong reducing agent. So without even doing calculation, we can say, yes, they will react, because the reason is because bromine is a strong oxidizing agent and silver is a strong reducing agent. If you want to extend your explanation, bromine is most likely to be reduced to bromide and silver is most likely to be oxidized to Ag+. Okay, so that's the first, I would say, method A. Okay, strong oxidizing agent reacts with strong reducing agent, which is silver, and the oxidizing agent is bromine. Okay, so you have to understand the question. When it says will bromine, you must identify the correct species of bromine. Bromine means Br2. Br minus is called a bromide. So please be careful, okay? Will it oxidize silver to silver ion? So silver is Ag, silver ion is Ag+. So most of the time, it is the formula that students get it wrong, okay? So write the equation for the suggested reaction. Okay, I'll skip step 1, actually. I will go to step 2. Write 2 half equations and include the E naught values. Okay, so I will start with, I will just label reduction and oxidation so you can see. Okay, so our reduction reaction, the species that is most likely to be reduced in this case is bromine. I hope you can understand why. Bromine will gain electrons to be reduced to 2 bromide. Okay, and then oxidation is the one with the less positive value. So Ag will be most likely to be oxidized to Ag+ and E-. Now, if you're wondering, how did I come up with that answer? Is because of the values. The more positive will go reduction, and the more negative will go oxidation. Again, even though it's not negative, it's less positive. Okay, so this is the half equations, and I will also write down the E naught values. So bromine, oops, I missed out my Br2. Bromine to bromide, the E naught value is reduction forward plus 1.07. silver to silver ions is negative 0.80. I have reversed it because I am looking at the reverse reaction. Okay, now when the question wants you to write down the equation, it means we are combining the oxidation and the reduction half equation. Okay, so this is what we call a half equation. When you add two half equations together, they become one. Okay, so a complete equation. Okay, so you can see that our number of electrons do not match. Okay, so we need to multiply. So here, note, need to multiply this half equation by 2. Okay, we times everything by 2 to give us 2Ag to form 2Ag plus 2 electrons. Then only you can see that the electrons released by the silver solid and the electrons gained by the bromine matches. Okay, so once the number of electrons on both half equations are balanced, we then add them. Okay, so how do we add equation? Same thing. Okay, so Br2 is my reactants plus 2 electrons plus silver to form my products. I should use the 2 silver, yeah, to form 2 Br minus plus 2 Ag plus 2 electrons. Okay, so if you're wondering where I got this, bromine plus 2 electrons comes from the reduction reaction. The 2Ag comes from the multiplied oxidation reaction to form 2 Br minus, which is the product of my reduction, and 2Ag plus 2E minus is the product of my oxidation after multiplying them. Okay, so remember, even though I've multiplied the half equation, the E note doesn't change. Okay, so actually you can skip a step here and just cancel, and just cancel out the electrons. Okay, so actually the overall equation is Br2 plus 2Ag to form 2 Br minus plus 2 Ag plus. Okay, this is why it is important for you to balance the electrons so that we no longer have any electrons in the full equation. Next, add the two voltages as combining the two half equations. So E cell is equals to E reduction plus E oxidation, which is 1.07 plus negative 0.80. And that is positive 0.27 volts. Okay, check if the value is positive or negative. If the if the E cell, not the E note, can you change that? If the E cell is positive, the reaction is feasible. If E cell is negative, the reaction will not occur. So the E cell is positive. Therefore, reaction is feasible. Okay, that's one reason. Another reason is because the first one that we did, bromine is a strong oxidizing agent, and silver, oh gosh, I don't have space. Silver is a strong reducing agent. Okay, so there's two method. Sorry, I will call this method A and method B. This was my method A. And this is my method B, which is via calculation. Okay, so if you want to copy this down, I will just zoom it out a bit so you can see and screenshot, hopefully. And I'm hoping that the audio is better this time. If you have any problem, please let me know. Any mistakes spotted, do let me know. Okay. So that is all for today. Assalamualaikum, and thank you, everyone.